So I think 1 hour is enough. Yes. Mhm. Okay. That is what should happen. Okay. When you are doing something, you can get idea. If you are doing something real, okay. If you are doing if you are doing something with yourself, then you can get idea. Okay. In the exam, normally you are doing the things by yourself. Okay. Then sometime maybe you get idea. Okay. Okay. So anyway, thank you for your feedbacks. Okay. Okay. So we will start our session. Okay. So I think 1 hour is enough to discuss the things. Okay. Okay. The first thing is, so I will take one example. Okay. I will take one practical example. Okay. So this is a practical session actually. Okay. This is a practical session. It is just like a lab. Okay. This is just like a lab. Okay. Uh, but some theoretical part also involved here. Okay. But this kind of things are included in normal signal and system labs. Okay. Okay. So I will. So let us take. Let's say that. Let's say that you have a turbine. Okay. What is turbine doing? You have a turbine like this. Okay. You have 3 turbines. This is the, I don't know the name, and this is other turbine. Okay. And this is the third turbine. Okay. So you have 3 turbines. Okay. So now you are rotating this axis. Then there is a magnetic field. Okay. And this conductor will cut the magnetic field and it generates a voltage. Okay. So I think maybe you can remember how a turbine or how a motor is working. Okay. It is uh, uh, the working principle is normally based on electromagnetic things. Okay. Magnetic things. Okay. So anyway, when this rotating, it will generate a sinusoidal signal. Uh, that is what we need. Okay. So let's say that this turbine will generate some sinusoidal voltage like this. Okay. I think CB also generate this kind of signals. No? In our electricity board, they are using turbines. Okay. To generate the power. Okay. So sometimes these turbines are rotating using water. Okay. And sometimes these turbines are rotating using steam. Okay. So anyway. Okay. So so anyway, we will get a voltage signal like this. Okay. So this is time and this is a voltage. Okay. Say that the rotating frequency is that means cycle per 1 second, that is frequency is 50 hertz. So this rotating frequency is 50 hertz and it will generate 2 volt 4 volt peak to peak signal. 4 volt peak to peak can means this is one peak and this is the other peak. Peak to peak means this the difference between these two. So that is 4 volt peak to peak. Okay. So this is our first signal. Say that second signal. Okay. Second signal also generate 50 hertz signal. Also generate 50 hertz signal. Okay. And it peak to peak is 8 volt peak to peak, say 8 volt. That means this peak will be 4 and this will be peak will be -4. Correct. And this third turbine will generate another sinusoidal wave. Okay. and it is also 50 hertz. Okay, let's say that it is 5 peak to peak voltage. That means this one is 2.5 and the lower peak is minus 2.5. So these are the three voltage signals. Okay, these are three voltage. Okay, now so here we have V1. Okay, this voltage is varying with time. Okay, so that is why I use this T. Okay, so this voltage is V2T and this voltage is V3T. Okay, so if I add these three frequencies, okay, if I add these three frequencies, okay, what is the output? Okay, before that, how can we add these frequencies? How can we add this voltage? Do you have any suggestion? Do you have any suggestion? I think if you are smart, you can you can imagine. At least you can imagine a method how to add these three. Okay. Actually, I think we no need any special circuit here. Any special electronic circuits? I couldn't understand. The, I couldn't understand your answer. Okay. So anyway, so say that so say that actually when you if you are coming to the lab, you can do this. Okay, you can do and try this. Actually, I haven't tried this, but I think it is possible. Okay, let's say that we have three signal generators. Okay, we have three signal generators, and we can generate this. We can create this kind of signal from this generator, and this kind of signal from this generator, and another signal from this generator. Okay, so in signal generator there is a port, no, there is a port. Okay, there is a port. Okay, and that port is a coaxial port, I think. Okay, so when you get it, you will get two cable. Can you remember the signal generator? I hope you have used this, no? Did you use signal generators? I think you have done some lab session for your electronics and electrical things, no? You have used the signal generators, oscilloscope, and power supply. Have you used? Tell me, maybe if you have used one more time, still you are not familiar with this instrument. Okay, if you use this one or two or three times or four times, maybe you are not familiar with this. Okay, so don't worry, I'm not going to ask any question. Okay, uh, can you tell me that have you worked with signal generators, oscilloscopes, and power supply things? Have you done any lab session? Have you attended any lab session? Yes, thank you. Okay. So I think maybe you can remember that in signal generator here you have a coaxial connector. Okay, that means the outer conductor is ground and the middle conductor is line. Okay, then you have to separate cable actually. To separate crocodile pin, can you remember that crocodile pin? It is just like this, no? Just like this, crocodile pin. These are called crocodile pin. Okay, like this. And these crocodile pins are connected to the cable. Okay, so you have two cable. One is ground, another is line. Okay, okay. So Okay, thank you. Okay, so okay, if I add, if I connect like this, okay, actually I haven't done this, okay. I haven't done this, but I think it will work, okay. If you have three generators, okay, three generators, here you have a ground cable, okay, here you have a ground cable, and here you have a line, okay. So you get this line and connect it to this second generator ground, okay. So this is line and this is ground, okay. Then this second generator line you will again connect it to the third generator ground, and you get the output, okay. So if you connect the oscilloscope between these two terminals, okay, if you connect the oscilloscope between these two terminals, okay, oscilloscope, what kind of signal do you expect to see here? I think so both these three signal will be added. Do you agree with me? If I connect this like this, can I add all the signal here? This one, this signal, this signal. There are three signal generated, three sinusoidal signal, V2, 3, V3. Okay. So if I connect all three generators like this, I think all the signal will be added at this point. Okay. So output of the third one will add at this port. I can get the added signal. Do you agree with me or not? Actually, I am also not sure. I think, but it is for example, these are voltage, time varying voltage. Okay, so if you have batteries, okay, tell me if you have three battery. If you have three battery like this, if you connect this battery like this, let's say that is this is 3 volt, this is 2 volt, 3 volt, and 4 volt. If you connect the battery like this in parallel, what is the voltage between these two terminals? Okay, so it will not 2 volt, 3 volt, or 4 volt, 4 volt. Another value will appear here, no? Okay, but it is not the addition value. I think we have to add the reciprocal. We have to add 2 volt, 5 volt, 1/3 volt, then 1/volt. Then we have to find this. So that is the value here. But if you have connect this battery in series like this, so this is 2 volt, 3 volt, 5 volt. What is the value between these two? It should be 2 volt plus 3 volt, 5 volt plus 10 volt, 5 volt plus 5 volt. You will be get 10 volt, no? Okay. Yes, 10 volt. Thank you, Mohammed. Okay. So you will get 10 volt here. Okay. So I think same is here, no? The only difference is this frequency are changing. This voltage are changing, but all internals voltages are already again adding. No? Let's if you consider time, okay, instant, that instantaneous value will add if you connect the oscilloscope, sorry, signal generator like this. So I think you will get this kind of uh, added signal. Okay, so I think in that way you can add these three signals. So here what you have to do is you have to connect the three turbines. So here plus, minus, plus, so you can get connected to the minus, and here this connected this plus connected to the minus. And if you get the output from here, you will get the added signal here, I hope. Okay, so I think the formal way is that, okay, formal way, you have to get the signal generator, okay, and you have signal, this signal generator means this can be a, turbine, okay, maybe it may be a turbine or something, okay, it may be a motor, or it may be a function generator, anything, okay. Anyway, if you get the signal generator, and if you connect it to the resistor, okay, and if you get the second one, and if you connect it to the resistor should be same, okay, and here also you have to get connect, should be connected with the resistor. Then you can add these three, okay, these three, and you can send, okay, you can send it to another R, the same R, like this, okay, same R like this, okay, and if you get the output here, you will get the added voltage, okay. How it can happen? Can anyone tell? Can anyone have idea? So you know that if here the current is going, here also the current is flowing, here also the current is flowing, okay. So this current is, these are not related with the signal and system, okay, I1, I2 plus I3, okay. Then this I1 is nothing but, if the voltage here is V1, it is V1 by R, V2 by R plus V3 by R. So this is the total I, okay. Total I means, okay, okay. So if this I is going through this R again, so it will generate the another voltage, no, V, okay. Let's say that that is VT, V total. So V total by R. This is the I, no? This is the I value, okay. So you can see that these are cancelled out, and you will get VT is equal to V1 plus V2 plus V3. Okay. So if you have connected it through a same resistance, okay, like this, again you will get the add-in voltage. So this is the formal way. Okay. This is the formal way. Okay. So I think uh, when uh, you are in a lab, you can see these things, okay. You can verify this, okay. So these things will develop some skills in you, okay. So try to do this, okay, when you are coming to the lab, okay. If you have done your the planned lab session quickly, you can do this kind of experiment, okay. And if you need, you can request, okay, you can request, uh, we need to use the lab, we have to do some experiment, okay, we need to use the lab. Then the SLTC will give you the permission to use the lab, okay. That is, it is your right, okay, it is your right, uh, because the labs are for student, okay. So you can use the lab at any time, but you have to first get the permission, because the SLTC should arrange some lab person, okay, to the session, okay. So it will take some time, okay. So before coming to the lab, you can ask permission, okay. This day we are coming, can we allow to use the lab, okay. If the lab is free at the request date, so you will be granted the permission, okay. So you can request, and you can come to the lab, and you can do this kind of things, okay. Please do this, okay, then you can get some idea, okay. So anyway, so how we can see this one, okay. So if we have oscilloscope, we can see it, but now we don't have oscilloscope, but we have MATLAB, and we will try to see it in MATLAB, okay. Actually, before coming, I write some I have wrote some uh, program, okay. So I can we can, because I'm typing very slowly, so if I type it in advance, I can save the time, okay. Okay, so okay, so let's say that so what is the value here? We get 50 hertz for peak to peak, 50 hertz, 50 hertz, 8 peak to peak, 5 peak to peak, okay. So these are the general value, okay. So V1T is 2 cos 50 hertz, 50t, okay. V2t is 4 cos 50t, V3t is 8 cos 50t. So we will see what happened to what kind of signal we will get here. Okay, we will see. Okay, so anyway, I will try it. Okay, I think it is easy. Okay, so first I think we have done some MATLAB, no? Okay, we have done some MATLAB as I can remember. Okay, I think we have done some MATLAB, no? I think all of you have MATLAB in your computer. So can you do this with me? Okay. First you define the time value. Okay. So these are the time value I have defined. Okay. So if this is not suitable, later we can change it. Okay. At this time I will use this one. Okay. So if you run this, okay, you will get this t, this variable, and it is array, no? So you receive array. Okay, I hope you have the basic idea, no? So actually this is not MATLAB session. Okay, I'm going to show you the things. Okay, so I will do this quickly. Okay, if you are not comfortable with this, I will do this MATLAB tutorial again. Okay, to get this idea. Okay, so this is a one way to define array in MATLAB. Okay, so likewise I can define array. Here I take some t values. Okay, so can anyone tell, is this t is continuous or discrete value? Is this, are these continuous value or discrete value? Can anyone tell quickly? Can anyone tell? Just type DOC. No need to type the total word. Just tell me these values are discrete or DO continuous. C, DOC. Just tell me. Just type. No. Anyway, actually that is not continuous value. Okay, these are discrete value. Why these are discrete? Because here you have anyway, thank you for the feedback. Okay, so here you have, so I have defined t like this: 0, 0.001 step to 3. Okay, then I will have first 0, then 001. So I have 001 step. So the second one is 002, 003, 0.004. Okay, likewise I will get up to 1, then 1.001, 1.002, I will get up to 2, then 2.001, I will get up to 3. Okay, so I will have this much of value. Okay, so if I count that, okay, if I count that, I will get 3001 3001 elements. Okay, values. Okay, so you can see if these are continuous, if I get the value between 0 and 1, okay, if this is continuous value, means between 0 and 1 all the values should be here. All the value means 0.001001. We don't know. Okay, because this we can define very little decimal value, no? Okay, we can define very decimal value. For example, 10 to the power minus 100,000, 10,000, 100,000, any value. Okay, so between this 0 and 1 there is infinite number of value. Okay, but here you have only how many values? 100 values. with 0 and 1, you have 100 values. You have 100 values because I will get 0, 0, 1, 0, 0, 1, not 100,000 value. You will get only 1,000 value. So that means it is a countable value. So these are discrete value actually. But we select them very, very, we get them very near points. Okay. So actually these are discrete, but we can see them as a continuous. Okay. We can see this as a continuous because the difference between two values is very small. Okay. Then you can see it as a continuous value. Okay. But these are not. In MATLAB we can't generate, in practically we can't generate continuous value. Okay. That is the truth. Okay. So I hope you get it. Okay. In practical we can't generate continuous value. We can only generate discrete value. But if we get the difference between two adjacent value is very low, you will see it as a continuous variable. Okay. But it is not truly continuous variable. It is a discrete value. Okay. Let's see. So now I have these three signal. Okay. So I write this signal like this. Okay. So first signal is, as I can remember, 2. Okay. Anyway, maybe the signals are not, maybe some point will be changed. Okay. But I will write this like this. Okay. 50 hertz T. Okay. Plus, then the second signal will be, as I can remember, it is 4 cos 50 T. Okay. Plus third signal will be 2.5 cos 50 T. Okay. 50 T like this. Okay. So this is our composite signal. So this is a composite signal. Okay. So this is a composite signal. Okay. So if I will use some brackets here also. Then I can isolate this one. Okay. If I use a bracket here, then I can isolate that term also. Okay. This is for safety. Okay. This is for safety. Okay. I think if you have any doubt, is any terms will corrupt with another terms, simply you can use a bracket. Okay. Okay. And I think here we have to use the product, the multiply this one. Okay. So this is the composite signal. Okay. Now if we add these three signal together, we will get this kind of signal. Okay. So if I plot this with respect to, now we have to first we have to put the independent variable. In our case, this is T, and then we have to put the dependent variable. This is X. Okay. So what do you expect here? Let's see. Okay. So if you connect this to a oscilloscope, you will get this kind of signal. Okay. You will get this kind of signal. Okay. So what are the things here you can observe? Okay. So let me reduce this time point. Okay. Let me take around 1. Okay. Here I am changing the scale. Okay. I just change the scale. Okay. Let's say we will get 0.5 or around 0.5 or something. I think then we can see our signal very clearly. Okay, now I think we can see. Okay, so what can you observe here? What is the frequency of this signal? What is the frequency of this signal? Okay, I think you can easily find that one. How to find the frequency? Okay, you know the period, no? So what is the period here? So this point is repeating here again. Okay, no? And this point is repeating here again. Correct? This point is repeating here again. So this point to this point, this is the period. This is the period. Okay, so this is the period. So if you can see that, what is the period? Period is about, if I scale, if I, let me reduce the scale. Okay, oh no, that is not okay. Because I can't get a full curve, no? I couldn't get a full curve. So I will get around 0.3, okay, 0.2 maybe. Yeah, we have a full curve now from here to here. Okay, so if you see that this is the time, no, this is the time value. If you get this point, approximately it is about 0.125. 0.125. Okay, so your T naught is 0.125. And if you want to find the frequency, what you have to do? If you want to find the omega naught, what you have to do? You are going to find the frequency. Okay, now you can find the period is as 1.125 second. Okay, so this is your period. Understand? If you have any problem, please ask. Okay, so from here to here, so I take this is one period, we can see it. Okay, because this value is repeating here. This is an approximation. Okay, this is not exactly. Okay, now I am going to estimate the frequency. Okay, so this point, okay, so this point will map to this point, no? So it will be about 0.125, maybe, yeah, 125, 1.3, I think 1.3, no? This is a middle, it will take 1.3, 0.13 maybe 125. Okay, let's take it 125. Okay, so how to find, if you know the period, how to find the frequency, omega naught? So you know that 25 by omega naught is equal to T naught. So you have omega naught is equal to 25 by T naught. Huh? So you can find the omega naught. Here you know the 25, and here you know the frequency period 0.125. So let's see what is the value here. Can anyone tell me what is the value? So we can use the MATLAB command prompt to calculate that value. Okay, I think you have seen that, you may have seen that I have done this to verify this. Okay, not for this case, but for the frequent the Fourier series value, I try to do this. Okay, so let me what we take 2 pi divided by 0.125. So what is the value here? So what is the value here? 50.265. Actually, this is 50 hertz. Okay, so this is the frequency of this signal, this composite signal. This is the frequency of this composite signal, and this is 50 hertz. Okay, so what is it equal to? It is equal to these three. No? All these three are 50 hertz. Okay, so you will get the 50 hertz resulting signal. Okay, so how many frequency components are here? Frequency component are here. Only one frequency component, no? Because it is 50 hertz. Okay, so you have with this signal, if you add, I think you get this. Okay, when after this session you can go through my recorded session, okay, theoretical one, then at that time also I think you can get idea, okay, about this. Okay, so if you already referred that, I think this time you will understand it clearly. Okay, if you refer the video, the two video I have, the example, Fourier series example video I have uploaded, then you can understand these things very clearly. But try to understand this at this moment, this thing. Then when you refer the video, you can clarify some doubts. Okay. Okay. So, uh, so what is your observation? What is our observation? If we have, if we add any number of sinusoidal signal, any number of sinusoidal signal with, so can you, I think you can't remember. So this is our observation. If we add any number of sinusoidal signal, okay, we get any number of sinusoidal signal with same frequency. With same frequency, we get a sinusoidal signal with the same frequency. Now, if we add 350 hertz signal, and we will get another sinusoidal signal with 50 hertz. Okay. So although I have added 3 signals, okay, I get one signal and it also have one frequency component. Okay. So that is the idea you have to take. Okay, I think it is clear. Okay. So now try, okay, if you change, okay, so if you can write this in your MATLAB, you can change this value, okay, the any value to any value, okay, 20, okay, and also you can add some phase shift here, maybe 5/2, okay, 5/2, maybe +2, any phase shift, okay, any phase shift you can add, but don't change the frequency. You can change the amplitude, you can change the phase shift, okay. So you know that if we consider a sinusoidal signal Vt, it is the form of a cos omega naught t plus 5, okay. So there are 3 main parameters: amplitude, frequency, and phase, okay. Amplitude, frequency, and phase. If you are not going to change frequency, and if you change this amplitude or phase to any value, the signal will not be changed, the frequency will not be changed, we will see it. Okay, so just add some add uh, any phase shift, okay. But if you get, so you will get the signal, same signal, but you will get some phase shift, the phase is shifting, but no affected to the frequency. Okay, the phase and amplitude can be changed. Okay, we can't say the same signal with the same frequency. Okay, the amplitude and phase can be changed. Okay, amplitude and phase can be changed according to the given amplitude and frequency. Okay, but the frequency will say, okay, and we will get a sinusoidal signal. Okay, we will get a sinusoidal signal with the same frequency. Okay, we can't say that other parameters are okay. Okay, but a sinusoidal signal with the same frequency, correct? So this is one thing you should understand. Okay, so did you understand this? Okay. Okay, so now, so okay, let me if I add, so okay, I have a power supply here. I have a power supply here, and I set that power supply to 5 volt. okay, 5 volt, and I add this to this signal also, okay. So I have at this 5 volt also, okay. So what is this? Okay, so these are some frequency, okay, these are some frequency, AC current, these are some AC voltage, these are AC voltage, and this is 5 volt is a constant one, so it is a DC voltage, okay. So it is a DC component, okay, it is a DC component, okay, it is a DC component. So how I can add the DC component? I just use a power supply and set it to 5 volt and add to this, okay. And here I get the power supply, okay, I get the power supply and I set it to 5 volt, okay. And in power supply also I have ground and line, okay. Then I connect this line to uh, the signal generator ground, okay. Then I I make the series connection like this. Then I connect the oscilloscope, okay, to here, okay. So what kind of change you will you will expect? Let's see, okay. So if I add 5 volt, okay, 5 volt, or maybe -5 volt, okay, maybe 10 volt, any value. If you add any value, the frequency will not change. If you add a DC component, frequency will not change, okay. Um, so if you want to add -5 volt, how can you do? I think you have get 5 volt. You can get the 5 volt from a DC supply. You can get the 5 volt from DC supply, okay. How can you get the -5 volt from a DC supply? Just tell me by one statement. Do you have idea? How can we? Very simple, okay. So here in signal generator, you have plus and minus, and also there is a ground port. Can you remember? There is a ground port. So if you get a jack, and if you ground this plus, okay. So in signal generator, you have a plus port, minus point, and ground point, okay. So if you if you ground this plus terminal to the ground, and if you set 5 volt, you will get the -5 here, okay. So like this you can generate -5 value, okay. If you connect it to directly to -5, what happened? If you connect this terminal to the minus terminal, what happened? It will short circuit, okay. So don't connect like that, okay. Please remember that you have to connect to the ground port, okay, not to the minus port, okay. If you connect directly to the minus port, it will be short, okay. But if you ground this port, and if you ground this port also, it will not short circuit, okay. You can try these things, okay. Uh, yeah, yeah, so maybe not, okay, maybe it will be short circuit. If you connect the board terminal to the ground, it will create a short circuit again, my code, okay. Anyway, okay. Okay. So I'm trying to give you a sense that this one has this subject has a practical smell, okay. This subject has a practical sense, okay. That is what I want to tell you, okay. Okay, so it will make interesting to the subject, I think, okay. So if I add any DC component, so the signal will not change, okay. Signal will not change, okay. Okay, but if you observe, you can see a DC shift, okay, DC offset. Okay, can you remember that there is a button in signal generator that's saying that DC offset or something. So actually, when you set that DC offset, some DC component will add, minus or plus component will add. Okay, so let me show you it. Okay, let's say this is X1. Okay, so I am going to plot this one again. Okay, plot Tx1. Okay, so and I can you remember that we have to put hold on command here. Otherwise, you will not see the both signal in the same graph. Okay, so I have to use the hold on. Then this X and X1 will give you in the same. So X, let me put blue, color blue. Okay, so this is the color, and X1, the DC shifted one, I will use red. Okay, I will use red. Okay, so if I run, okay, can you see that this is the original signal, blue one, and when I add the DC shift, it is shifted above like this. Okay, so it is DC offset to plus side. Okay, so if I add -5, as you can use the method. Okay, you can ground the plus button, you can connect to the ground, you can connect to the -1 to the ground, correct, the ground of the signal generator. Okay, so you can see that. So see, this is our original signal, and the DC shifted signal is shifted to downside. Okay, so what I want to tell you is that if I add any DC component, it will not get any corruption. Signal will be a sinusoidal signal with the same frequency. Okay, any signal plus DC component, we get a sinusoidal signal with the same frequency. Okay, so what if we change the frequency? Let's change one frequency to 25 or something. Let's see what happens. So I remove this X1. Okay, I remove this one. So can you see that now the signal is changing? Okay, so if I get some other circle, let me take T up to 2. Can you observe this? Can you observe this? So this is not a sinusoidal signal, no? So you can see that this is not a sinusoidal signal. Here, this part is somewhat distorted, no? Okay, let take another frequency also. Take about 2, maybe 2. I think we can see the effect very clearly. Let's take 10. Okay, see, okay, so that one also okay. Okay, if you put 2, that one also okay. Okay, okay, so see, if you change the frequency, okay, if you change the frequency, so it will be not a sinusoidal signal. Okay, so if you add different frequency, okay, it will create a different signal. It is not a sinusoidal signal. Okay. So so that this is the most important thing you should understand. Okay, so here How many frequency component in this signal? Can you tell me? How many frequency component in this signal? Can you tell me? Please tell me how many. I think we are running out of time. Okay. I hope I can complete this within 1 hour, but I think I get more time. Can you tell me how many frequency component are here? How many frequencies? Tell me someone how many? One, two, three, five. Any number of frequency component? How many frequency component do you think? Tell someone. No, not six. Not six. Okay. Anyway, thank you for the answer. Yeah. Yeah. Actually, that is the answer I expect from you. Okay. So if you give me that answer, you understood this up to some level, but that is a wrong answer. Okay. Again, see and tell me how many frequency component. I am not asking the signal. How many signals are there? I am asking how you tell the signal, number of signal. Okay. Very good. You tell the number of signal. There are three signals. We add three signal together. Okay. But what are the frequency component? What are the frequencies involved with this signal? How many frequencies involved with this? How many frequencies are there? There are three signal actually, three sinusoidal signal. Okay, two this sinusoidal signal. Yes, thank you. There are two frequency, no? Okay, I hope you get the understanding now. Okay, you are understanding this subject gradually. Okay, because I didn't get this kind of answer previously, but now I get some answers. Okay, so I hope that is a good mark. Okay, so here in this signal you have two frequency component actually. One is 50, so this is 50 and this is 10. Okay, we add. Okay, here we add. Here we add cos 50t, cos 50t, and cos 10t signal. So these three signal we had. Okay, and there are some amplitude. Okay, there are some amplitude, and maybe there are some phases also. Okay, but we add this 50, 50, and 10. Okay, so these are the frequency component. So in this signal, you have two frequency component. Okay, in this signal, you have three frequency component. When you add three frequency component, it will not a sinusoidal signal. Okay, so it will be another form of signal. Okay, okay. So let's take another DC value here. Let's add another DC component. Okay, so we will see what happens. Okay, same signal, but the DC shifted. Okay, but it is still not a sinusoidal signal. Okay, so if you add more component here, let's add another signal. Let's say that it is. I will take one this. Okay, let's say it is 25. Okay, and I will take another one also. Okay, so I add some another frequency component also. Okay, and it is let's say it is 20 or something. Okay, so what kind of signal we get? Let's see. So now you can see that the pattern is changing, no? Okay, so pattern is changing here. Okay, so can you see that when we are adding some frequency component, when we are adding some frequency component, okay, frequency component, the uh, the shape of the signal is changing. Okay, shape of the signal will be changing. Okay, so did you get it? Okay, so that is very important to understand. Okay, when you are adding more and more frequency component in this signal, we have 20, 25, 50, that means 3 frequency component, and 10, that means we have 4 frequency component. Okay, now our signal is changing. Okay, but it is a repetitive signal. Okay, but it is a repetitive signal. So if you change this up to 5 or something, you can see it. See, this is a repetitive signal. No, signal is repeated. Okay, but it will take different pattern. Okay, different pattern. Okay, so what is the observation you can take? Okay, actually this is the Fourier series. Okay, uh, this is the understand. Okay, so what happened if we add more frequency component, what happened? We get different pattern. No, we get different pattern.